The topic of today's lecture is number synthesis. During this stage of kinematic synthesis called number synthesis, we determine the type and number of different types of links and the number of simple pairs like revolute or prismatic pairs that are needed to yield a single degree of freedom planar linkage. It is needless to say that all these single degree of freedom planar linkages will satisfy the Grubler's criterion which were discussed earlier. However, before we get into the discussion or details of number synthesis, we shall first prove certain basic results which are of vital importance for number synthesis. The first of these two questions is, what is the minimum number of binary links that such a linkage must possess? So, we determine the minimum number of binary links in a single degree of freedom planar linkage. Let n is the total number of links in the linkage and n2 be the number of binary links, n3 be the number of ternary links, similarly n4 be the number of quaternary links, and so on. Thus, we have the total number of links n is equal to n2 plus n3 plus n4 up to ni, where I denotes the highest order link that is present in this linkage. So, our first task is to determine the minimum value of n2. Towards this goal, let us consider this figure. In this figure, we see there is one link which is connected to two other links through the revolute pairs here and here. Now, to note that at each of these revolute pairs we have two elements, say 1 minus, which is the spin which goes into the hole which is denoted by 1 plus. So, this 1 plus and 1 minus we shall call elements. Thus, at each revolute pair we have two elements. Similarly, the two elements at these revolute pairs are this 2 plus and 2 minus. In this way, if we count the total number of elements, that I can write E should be equal to twice the number of joints or pairs j, that is E is equal to 2j. We can also count this number of elements from these links. This is a binary link which has two elements because it is connected to two other links through revolute pairs. Similarly, a ternary link will have three elements because it will connected to three other links, and a quaternary link will have four such elements. So, if we count the total number of elements from the viewpoint of links, then I can write E should be equal to 2n2, where n2 is the number of binary links, plus 3n3, where n3 is the number of ternary links, plus 4n4, where n4 is the number of quaternary links, and so on, and ni, where ni is the number of ith order link. So, we have just now seen that the total number of elements can be counted from two viewpoints. If we count it from the viewpoint of number of pairs, then I can write the total number of elements E is equal to 2j. But if we count the number of elements from the viewpoint of different links or having different orders, then we can write that the total number of elements E is equal to 2n2 plus 3n3 plus 4n4 plus ini. Now, we can equate these two number of elements counted from the viewpoints of the kinematic pairs and from the viewpoint of different order links. We can write 2j is equal to 2n2 plus 3n3 plus 4n4 plus in I. As already told that all these linkages must satisfy the Grubler's criterion, which is 2j minus 3n plus 4 equal to 0, where j denotes the number of kinematic pairs and n denotes the number of total links. Now, substituting E equal to 2j, which we have just now seen to be given by 2n2 plus 3n3 plus 4n4 up to in I, minus we replace this n by the number of counts of different links, which is n2 plus n3 plus n4 up to ni. Simplifying this equation, we can see that 3n3 cancels, and ultimately we get n2 is equal to p minus 3 summed over all values of p starting from 4 up to I plus 4. That means n2 is given by p minus 3, p going from 4 to I plus 4. That means this p denotes the number of quaternary links and higher order links. So you can easily see, even if this sum is 0, the minimum number of binary links n2 minimum is equal to 4. This again convinces us what we have seen earlier, that the simplest linkage must have 4 binary links, what we call 4-bar linkage. Next, we would like to address another question, that is, what is the highest order link in an n-link mechanism? That means the total number of link is n, then in such a linkage, what is the highest order link? We shall try to answer this question in a reverse manner. We will say, let the highest order link be ith order. That means we have some ni's. Then what is the minimum number of links that is needed to produce a single degree of freedom planar linkage? Towards this goal, let me consider the following figure. In this figure, we start with a link with I hinges. This is the link which has I hinges numbered as 1, 2, 3, 4, so on up to I. Now, to produce a chain, at each of these hinges we connect another link. Like at the first hinge we connect link number 1, at the second hinge we connect link number 2, at the third hinge we connect link number 3, and so on, and this ith link at the hinge number I. Now, to connect these two links 1 and 2, we must have some motion transfer links. Accordingly, this I plus 1, I plus 2, I plus 3, so on up to 2I minus 1. The thing to note that at the hinge number 2, 3, 4 up to I minus 1, we have ternary links, because link number 2 has 3 hinges here, here, and here, and that is true for all other links connected at hinge number 3, hinge number 4, and so on. Because if we have a binary link at 2, then this particular hinge will not remain a full hinge, because 3 links, namely I plus 2 and another link and link number 2, will get connected at this higher order hinge. To retain this hinge as a simple hinge, all these links starting from number 2, 3, 4, and so on up to I minus 1 must be ternary links. So, we have produced a closed chain minimum number of links if we start from a link with of ith order, that is with I hinges. Now, let me count total number of links n. We have started with, I have already shown the number up to 2I minus 1, and you count the starting link which having I hinges, so the total number of links is 2I. So, thus we see that if there is an ith order hinge, then minimum I need 2I number of links to produce a closed chain. That means total number of links is n, then I max can go up to n by 2 and not more than by 2. I emphasize that this is the possible value of I max, not necessarily I max has to be n by 2. Definitely, it cannot be more than n by 2. Next thing we have to prove that this closed chain, from this closed chain, if I hold one link fixed, it must produce a single degree of freedom mechanism. That is, this particular closed chain must satisfy our old Grubler's criterion. For that, we count n is equal to 2i. Now, let me count the number of hinges, j. We have started with I hinges on this initial link. So, j is I plus, there is one hinge here and there is another hinge here, which is I plus 2 plus on all other links 2, 3, 4, there are 2 extra hinges because these are all ternary links. One of the hinge has been already counted with this starting link. There are 2 extra hinges on each of the links. So, that into I, how many such linkages? How many such links? We have started from 2 to I minus 1, that is 2 into I minus 3. So, that is the total number of hinge I plus 2 into I minus 3, which will give us 3I minus 4. So, we see that in this closed chain, the total number of links n turns out to be 2, where I denotes the highest order link in this chain, and the total number of joints j turned out to be 3i minus 2. So, if we write the Grubler's criterion, that is j minus 3n plus 4, we get 2 into 3i minus 2 minus 3 into 2i plus 4, which is 0. Thus, the Grubler's criterion is satisfied by this closed kinetic chain, and consequently, this can constitute a single degree of freedom planar linkage. So, we concentrate on these two results that we have just now derived. One is that the minimum number of binary links in a linkage must be 4, and the second is that highest order link mechanism, that is I max, is n by 2. Since all the single degree freedom linkage must satisfy Grubler's criterion, that 2j minus 3n plus 4 is equal to 0. That gives 3n is 2j plus 4. Now, we note that the right hand side 2j plus 4 is an even number, and if 3n is equal to an even number, then the n must be even, which means all the planar linkages, simple pairs and single degree of freedom must have even number of links. We have already seen that the 4-link mechanism is the simplest mechanism. So, the next more complicated mechanism should be n equal to 6, that is a 6-link mechanism. If the kinematic requirements are a little more complex, which cannot be satisfied by a 4-link mechanism, then we have to try to use a 6-link mechanism. Now, let me go into this number synthesis of 6-link mechanism. With a 6-link chain, we have n is equal to 6, that is I max is n by 2, that is 3. So, the highest possible is a ternary link. So, a 6-link mechanism constitutes of binary links and ternary links. So, the total number of link n equal to n2, that is the number of binary links, plus n3, that is the number of ternary links, is equal to 6. Now, for n equal to 6, we know to satisfy Grubler's criterion, 2j must be equal to 3n minus 4, that is 3 into 6 minus 4, which is 14, that is j is equal to 7. Now, we have got one equation, numbered equation 1, in terms of two unknowns n2 and N3. So we derive another equation involving N2 and N3 by counting the number of elements. The number of elements E is given by 2J, which is also given by 2N2 plus 3N3. Thus, 2N2 plus 3N3 is equal to 2J. With J equal to 7, this turns out to be 14. This is the second equation involving these two unknowns, namely N2 and N3. Our previous equation was N2 plus N3 equal to 6, and the second equation is 2N2 plus 3N3 equal to 14. We can easily solve two linear equations in two unknowns, namely N2 and N3, as N2 equal to 4 and N3 equal to 2. Thus, a 6-link mechanism has 4 binary links and 2 ternary links. Now, we shall see what are the possible combinations of these binary and ternary links to generate a 6-link, different types of 6-link mechanisms. This figure shows one possible 6-link chain with 2 ternary links and 4 binary links. As we see, the link number 1 is a ternary link, link number 4 is another ternary link, whereas link number 2, 3, 5 and 6 are all binary links. The thing to note that in this chain there are 6 link and 7 revolute pairs. 6 we can count at the vertices of this hexagon and 1 inside the hexagon. Another thing to note that here the 2 ternary links 1 and 4 are directly connected by this revolute pair, and all the 4 binary links are connected to the ternary links. This chain is known as Watt's chain. So, in a Watt's chain, 2 ternary links are directly connected to each other. In this Watt chain, we can see that the 2 ternary links, that is number 1 and 4, are equivalent, in the sense both of them are connected to a ternary link at one kinematic pair and two binary links at the other 2 revolute pairs. Like 4 is connected to link number 4 by a revolute pair, 5 is a binary link, 4 is connected to another binary link 3 at this revolute pair, and is connected to the ternary link 1 at this revolute pair. Exactly the same thing happens for link number 1. It is connected to ternary link 6, this revolute pair, and to binary link 2 to this revolute pair, and to ternary link 4 by this revolute pair. Thus, topologically, there is no difference between link number 1 and 4. The same is true for all binary links, namely 2, 3, 5 and 6, each one of which is connected to a ternary link at one end and to a binary link at the other. For example, link number 2 is connected to a ternary link at one end and to a binary link at the other end. And the same is true for all other binary links. Thus, there are 2 types of links, ternary links and binary links. But both the ternary links are equivalent, and both the binary links, not both, all the 4 binary links are also equivalent. So, from a Watt's chain, by kinematic inversion, that is depending on which link we hold fixed, we can get 2 different types of Watt's mechanism. One type of Watt's mechanism we can get by holding a binary link fixed, doesn't matter which one, 2, 3 or 5 and 6, because all of them are equivalent. And the second type of Watt's mechanism we can get by holding one of the binary links, that is either 1 or 4 as fixed. We will now show a model of a 6-link Watt's mechanism where we will find that one of the binary link is held fixed. As an example of Watt's mechanism with a binary link fixed, let us go back to our old example of this parallel jaw plier. We hold this lower jaw, that is this blue link, fixed. This is a binary link because it has 2 revolute pairs. Now, let us note that this binary link is connected to another binary link at this revolute pair and to this ternary link at this revolute pair. This lower handle is a ternary link because it has 3 revolute pairs, and this small link is another ternary link which has 3 revolute pairs. And these 2 ternary links are directly connected. So it is one type of Watts chain where we know 2 ternary links must be directly connected. Now, if we hold this lower jaw fixed, then we are holding this binary link fixed. We should also note that this is a binary link, this upper jaw is a binary link, and this yellow link is another binary link. This binary link is connecting this ternary link and this binary link. As a result of this, we get a Watts mechanism from a Watts chain. This is Watts mechanism of one kind. Later on, we will see Watts mechanism of another kind where a ternary link will be held fixed. As an example of another type of possible Watts mechanism, let us consider this figure. Here, as we see, we started from a Watts chain which has 2 ternary links 1 and 4 and 4 binary links 2, 3, 5 and 6. Now, here it is the ternary link 1 which is held fixed, and this is known as Watts walking beam engine. In this Watts walking beam engine, we must see that in the chain we have shown a revolute pair between 1 and 6 which has been replaced by a prismatic pair between this cylinder and the piston. But in our analysis, we always treated revolute pair and prismatic pair as equivalent. So, here as we see that this great beam, that is link 4, is connected to ternary link directly by this revolute pair. So, this is another type of Watts mechanism which is possible to get by kinematic inversion from a Watts chain. As another example of a 6-link mechanism with 7 hinges, we can get the following figure. Here as we see, there are 2 binary links, namely 2 ternary links, namely 1 and 4. However, unlike in a Watts chain, these 2 ternary links are not directly connected to each other, rather they are connected via this binary link number 6. So, here we have 2 ternary links 1 and 4 which are connected via binary link 6, binary link 5 and by 2 binary links, namely 2 and 3. And this particular chain where the 2 ternary links are not directly connected is known as Stephenson's chain. So, we see that in a Stephenson's chain, the 2 ternary links are not directly connected. But in a Stephenson's chains, the ternary links 1 and 4 are equivalent in a sense that both 1 and 4 are connected to 3 binary links at these 3 revolute pairs. For example, 1 is connected to binary link 6, binary link 5 and binary link 2 at these 3 revolute pairs. And link number 4, the other ternary links, is also connected to 3 binary links, to link number 5 here, link number 6 here and link number 3 here. Thus, both these ternary links are topologically equivalent because both of them are connected to 3 binary links. However, so far the binary links are concerned, there are 2 varieties, namely 5 and 6 and 2 and 3. We should note that both 5 and 6 are connected to 2 ternary links at 2 joints. 6 is also connected to 2 ternary links at 2 joints. However, link number 2 and 3 at one end is connected to a ternary link, but at the other end is connected to a binary link. So, there are 2 types of binary links they can be grouped as 5, 6 and 2, 3. So, by kinematic inversion, we can get 3 different types of Stephenson's mechanism, depending on whether the ternary link 1 or 4 is held fixed, or one of the binary links in this group, that is either 5 or 6 is held fixed, or one of this group, namely 2 and 3, that is either 2 or 3 are held fixed. So, there are 3 possible different types of Stephenson's mechanism which can be obtained by kinematic inversion from the same Stephenson's chain. We will now see a model of a Stephenson's chain to generate a Stephenson's linkage where a ternary link is held fixed. Let us now look at the model of the Stephenson's mechanism where one of the ternary link is held fixed. Here we have this fixed link as the ternary link, which has 3 hinges, one here, one there and another there. And this is the other ternary link which is connected to the fixed link by 2 binary links. So, the 2 ternary links are not directly connected, they are connected via binary links at these 2 points and by 2 binary links at this point. This is a binary link, this is a binary link. These binary links are equivalent because at one end this binary link is connected to a ternary link, at this end this binary link is connected to another binary link. Similarly, this binary link is connected to a ternary link at this end and to a binary link at this end. So, these 2 binary links are of same nature. Similarly, these 2 binary links are also of same nature because they are connected at both ends to ternary links. So, one of the ternary link is held fixed and we get one variety of a Stephenson's linkage. As another example of a Stephenson's linkage, let us consider the same Stephenson's chain and consider one of the binary links to be fixed. As shown in this figure, this is the Stephenson's chain that we have considered earlier, and in this chain, if we hold a binary link, say link number 2 fixed, then we get this mechanism. As we see, 2 is connected to ternary link 1 and link 2 is the fixed link, which is connected to a binary link 3 and to a ternary link 1. Link number 4 is the other ternary link, which is connected to link 3 here, link 6 here and link 5 here. This is known as Stephenson's valve gear mechanism, which is used in a steam engine. So, we have seen 6 link chains which consist of 4 binary links and 2 ternary links and various combinations which are possible as Watt's linkage or Stephenson's linkage. Let me now consider the next higher order link possible to give you the flavor of number synthesis. Obviously, the next more complicated mechanism we consider with n even is an 8 link mechanism, that is n equal to 8. Consequently, highest order link possible in an 8 link mechanism, that is I max, is equal to n by 2, that is 4. So, a 8 link mechanism will have binary link, it is possible to have ternary link and it is possible to have quaternary link. If the number of binary links is n2, the number of ternary links is n3 and the number of quaternary links is n4, then the total number of links n, which is equal to n2 plus n3 plus n4, is equal to 8. This is our first equation to determine n2, n3 and n4. We also know that the number of elements E, which is given by 2j, is equal to 3n minus 4, so that Grubler's criterion is satisfied, which means 3 into 8 minus 4, that is 20. Now, counting the number of elements from the viewpoint of links, we can write 2n2 plus 3n3 plus 4n4 is also equal to 20, because this is also equal to the number of elements. So, this is our second equation 2. It may now appear that we have 3 unknowns n2, n3 and n4 to determine, but we have only 2 equations, namely 1 and 2. Thus, there may be infinite solutions. A little thought would convince us that is not the situation. We still have finite number of solutions, because we should remember all these numbers n2, n3, n4 are integers. Not only that, the minimum value of n2 is also 4. Number n2 can start from 4, then can go up to 5, 6 and so on. Let us see what are the various solutions possible to these 2 equations under such restrictions that all these numbers n2, n3, n4 must be positive integers. There is no point having a negative number for the number of links, and also that minimum values of n2 is 4. So, for an 8-link mechanism, we have got 2 equations, namely n2 plus n3 plus n4 is 8, and 2n2 plus 3n3 plus 4n4 is equal to 20. So, if we assume that the values of n2 is 4, then from these 2 equations we get n3 plus n4 equal to 8 minus n2, that is 8 minus 4 is equal to 4. And from the second equation we get 3n3 plus 4n4 is equal to 20 minus 2n2, that is 20 minus 2 into 4 is equal to 12. Now, we get these 2 equations to solve for n3 and n4, and the obvious solution is n3 equal to 4 and n4 equal to 0. That means we can get an 8-link mechanism consisting of 4 binary links and 4 ternary links. There is no necessity that we must have a quaternary link. However, if we take n2 equal to 5, then we get n3 plus n4 is equal to 8 minus 5, that is 3, and 3n3 plus 4n4 equal to 20 minus 2n2, that is 20 minus 2 into 5 equal to 10. Solving these 2 equations, we get n3 equal to 2 and n4 equal to 1. Thus, we can also have an 8-link mechanism with 5 binary links, 2 ternary links and 1 quaternary links. Similarly, if we take n2 equal to 6, one can easily find that we will get n3 equal to 0 and n4 equal to 2. That means we can have an 8-link mechanism with 6 binary links and 2 quaternary links. Now, from these 3 different types of 8-link chains, by kinematic inversion, one can get a very large number of different mechanisms. In conclusion, let me now repeat the 4 most important points that we have learned today during this discussion of number synthesis of planar linkages. The first point is that the minimum number of binary links in any such linkage must be 4. That means we must have at least 4 binary links. The second point is that the highest order link in an n-link mechanism is n by 2. That is, in a 6-link mechanism, the highest order is ternary. In an 8-link mechanism, the highest order is quaternary. Third thing we have seen that the total number of links must be even. And the last point is that with increase in the number of total links, the possible types of various mechanisms that you can have from such chains by kinematic inversion increases drastically.